to share this with you all, and I'm sorry not to be there in person. I hope the situation will be different soon. Okay, and so the first portion of what I'm going to say is a lot of it is going to repeat things that Michael said in the last talk. So bear with me, but I hope maybe I'll share things from a slightly different point of view. And if you, yeah, so I tend to learn things very slowly, and it helps to hear things multiple times. So hopefully for some of you, this is okay. All right, so let me try to put what's happening in context. So we're going to study the cohomology of some moduli space, and so why should we study cohomology of moduli spaces? Well, maps to moduli spaces are giving families of objects that are parametrized by the moduli space, and so cohomology of the moduli space will be characteristic classes of those families. And the sort of first example you should think of is projective space, which is, say, lines through the origin in Cn+1. And a family of lines is a line bundle. And so on Pn, there's a tautological line bundle. And it has a characteristic class, which is the first Chern class. And so let's call that X. And then the cohomology of Pn, well, it has to have X in there. So there's Q adjoin X. And then the degree of X is 2, because it's the first Chern class. And Pn has dimension 2n, so x to the n plus 1 vanishes for dimension reasons. And so here we have a tautological generator, and we have a sort of obvious relation. And then the beautiful theorem is that that's the whole picture, that everything is generated by X, and the only relation is the geometrically obvious one. And then you should note that if we could increase n, and the cohomology ring in some sense stabilizes in a way that we could make precise, and I won't, stabilizes to Q adjoin X as n goes to infinity. I hope that's sort of at least algebraically clear. And the next moduli space one could think of, which is the Grassmannian. So this is the set of so k-planes, so k-dimensional subspaces of Cn. And this has a tautological rank k vector bundle. So the fiber over a point is that subspace, and this has its Chern classes. So we have, so let's say that yi is Ci of V, and so then we could look at the cohomology of the Grassmannian. And so, well, it has y1 through yk in there. And so notice that now the degree of yi is 2i. So we have generators in some different degrees. And there are some relations, and well, some of the relations come from dimension, but in fact, you can understand all of the relations by observing that the tautological bundle sits in a short exact sequence where the center term is a trivial bundle. And so since the Chern classes of that center bundle are trivial, that gives some relations on these Chern classes. And in the theorem, again, is that all of the cohomology is generated by these tautological classes that sort of obviously have to be there. And then the relations are coming from something sort of obvious in terms of the moduli structure. And again, so this is now going to stabilize. So if we fix k and let n go to infinity, so this stabilizes to Q adjoin y1 through yk as n goes to infinity. So I haven't explained to you in detail what the relations are, but the relations sort of go away in the sense that they live in higher and higher degrees as n goes to infinity. So, okay. And then, so then the moduli space we want to talk about today is, so MG. So this is the space of isomorphism classes of smooth projective curves of genus G. And we'll always assume that G is at least 2. And so this is, you can think of it as a manifold. It's a smooth orbifold or Deligne-Mumford stack. So of complex dimension 3G minus 3. And so it's a moduli space, and so it has a universal family. So we have C to MG, so there's a universal curve here. Okay, and that doesn't yet, okay, so we want to describe what are some cohomology classes that just obviously come from this modular structure. So there's a line bundle, which we'll call omega, so a line bundle on the universal curve. And so you could take the relative tangent bundle, so at each point you take the tangent space to the fiber, but for various reasons, we'll take the relative cotangent bundle, so the dual of the relative tangent bundle. And so then, so now we have a degree 2 class on the universal curve, which is the first Chern class of this line bundle. And what can we do with that? Well, we can take powers of that or polynomials of that, and then we can push them forward. And that's the only thing that we can do from what we've described so far. So let's say that kappa I is the push forward of the first Chern class of omega to the I plus 1. Okay, so push forward, we're integrating along a real 2-dimensional fiber, so that will drop degree by 2. So the degree of kappa I is 2I, and hence the notation. And so then there's the, so Mumford made what I think at the time was a somewhat audacious and very, very optimistic conjecture, which was that as G goes to infinity, so in analogy with the Grassmannian, so as G goes to infinity, the kappa i's should account for all of the cohomology, and there should be no relations among them. So that was the conjecture of Mumford. So, so that was the cohomology of MG stabilizes to Q adjoin kappa 1, kappa 2, kappa 3, and so on. So as G goes to infinity. So here again, so now we have a polynomial ring now in infinitely many variables in increasing degrees. And so this means that if you fix a cohomological degree K, then for large enough G, the cohomology in degree K will agree with this ring. And that is, so this was a theorem, so famously proved by Madison and Weiss in 2007, building on work of many others. So John Harrer was the one who proved that the cohomology eventually stabilizes. And then a deep result of Ulrike Tillman proved that that what it stabilizes to is the cohomology of an infinite loop space. And then Madison and Tillman made a conjecture about which infinite loop space it should be, and if you know which infinite loop space it is, then you can compute the cohomology of that infinite loop space. So Madison and Tillman had a conjecture for which infinite loop space that implied Mumford's conjecture. And then what Madison and Weiss did in 2007 was they proved that that conjecture was correct. And so here, so something sort of wild happened, that things got connected to infinite loop spaces and stable homotopy theory. And I think this is one of the things that I find so compelling about the subject, is that different branches of mathematics all seem to converge and come together and interact in interesting and surprising ways with the cohomology of MG as a central focus. And so let me mention that there are sort of several different perspectives in which the cohomology of MG shows up in a very natural way. So I'm coming from algebraic geometry. I'm describing it as the cohomology of this algebraic variety or Deligne-Mumford stack. But MG is the quotient of Teichmuller space by a nice action of the mapping class group. And so this is the group cohomology of the mapping class group of a compact orientable surface of genus G. And so that's a perspective where this ring shows up from the point of view of combinatorial group theory or geometric group theory. And so the mapping class group is the component group of the oriented diffeomorphism group of a compact orientable smooth surface of genus G, and the connected component of the identity is contractible. And so this is also the cohomology of diff plus, so the cohomology of this infinite dimensional Lie group. And so that's the perspective from which homotopy theory enters. Okay, and okay, so Mumford conjectured that it stabilizes. It does stabilize, and it stabilizes in degrees up to about 2/3 G. And the real dimension is 6G minus 6. The virtual cohomological dimension is 4G minus 5. So there's a large unstable range. And but you could also look at, well, if we think about what happened on projective space in the Grassmannian, the tautological classes generated everything. But then there were just some extra relations that happened when the parameter n was small. And so one natural thing to study here is the subring generated by these kappa classes. So by the Madison-Weiss theorem, we know that there are no relations up to degree 2G/3, but then there will be some relations. And so this has been studied by many people, Faber, Pandey, Loyenga, Pixton. Many people have studied this. It is supported in degrees less than or equal to 2 times G minus 2. It's one-dimensional in the top degree. And one thing I should mention is that everything here, so all these kappa classes have even degree. So the tautological ring is supported in even degrees. And okay, so one sort of has to work harder to find odd cohomology, that all of the cohomology that's coming directly from these tautological constructions is in even degrees. And maybe I should also say here that the tautological ring is all pure weight. So each of the different perspectives that we have on the cohomology of MG comes with its own advantages. And one of the advantages of looking at the cohomology of MG as the cohomology of an algebraic variety is that it comes endowed with extra structure. And so one part of that extra structure is a mixed Hodge structure. So there's an increasing weight filtration, a decreasing Hodge filtration. Pure weight means that it appears in the associated gradient of the weight filtration in weight equal to the cohomological degree. So the weight of kappa I is 2I, equal to the degree. And that's going to be important as we go on. So maybe I should just say sort of, so that algebraic structure, so viewing MG as an algebraic variety, so we have this weight filtration. So now we can try to answer questions about the cohomology of MG, such as, does the cohomology vanish or not in some degree? Well, we can prove non-vanishing in some degree by proving non-vanishing of one graded piece of the weight filtration. So we can try to answer questions about the cohomology of MG, one graded piece of the weight filtration at a time. And so maybe I should say here, so this tautological ring, so we have one generator in each even degree. And so then the dimension of this tautological ring, well, the dimension of this ring in a given degree, that's just some partition number. So we're counting partitions of an integer, and we can estimate the partition function by the circle method. So that goes back to Hardy and Ramanujan. And so you can pretty easily bound the dimension of the tautological ring. So it's big O of some constant to the square root G. So it's super polynomial, but sub-exponential growth. And as Michael mentioned, so Haar and Zagier gave an exact formula for the orbifold Euler characteristic of MG, and then they estimated the difference between the orbifold cohomology and the ordinary cohomology. And that's an inductive argument that the twisted sectors, so the loci where there are automorphisms, look like things that are built out of moduli spaces of curves of lower genus with marked points. And so if you know something about Euler characteristics on those smaller things, then you can bound the difference between the orbifold Euler characteristic and the topological Euler characteristic. And so in this case, they were able to show that there's no cancellation of leading terms, and so the two have the same growth rate. So chi of mg looks like -1 to the g plus 1. Maybe what I should really say is that -1 to the g plus 1 chi of mg behaves like g to the 2g. So it's eventually alternating sign and growing super exponentially, super factorially. The Euler characteristic is negative for all even g at least 8. So we know there's lots of odd cohomology out there. And at the time that Haar and Zagier proved this, there were no known pairs k and g where k is odd and hkmg is not 0. And as Michael said, this means that there is sort of lots of cohomology out there that is not in the tautological ring. And in fact, there's sort of vastly more. And so that's what we'll call the unstable cohomology. And examples of unstable cohomology. So at the time that Haar and Zagier wrote this, in fact, the only known non-zero cohomology groups on MG were generated by kappa classes. So the first example came a few years later. So H6M3 is Q. And so this was a computation of Lehenge in 1993. And the way progress had been going was that progress was made by completely computing the cohomology ring of MG for some G. So Lehenge computed the cohomology ring of M3 with its full mixed Hodge structure. And so this H6 happens to have weight 12. Okay, so it's not of weight 6, and so it is not a polynomial in the kappa classes. Also, it's in a degree too large for G equals 3 to be in the tautological ring. And then H5M4 is Q. So this was computed by Tomasi. So again, Tomasi computed the full cohomology ring of M4 with its mixed Hodge structure and found that H6 has rank 1 and weight 6. So definitely not tautological, it's in odd degree. And that's it. We still don't know the cohomology ring of M5. Okay, so that's as far as that line has gone so far. I hope that before too long we will know the cohomology of M5, but the cohomology of M6. I mean, you can see the pace of progress that we get sort of one genus every 10 to 15 years, maybe 20 years. Okay, so but we can make more progress by looking at one graded piece of the weight filtration at a time. And as you may have gathered from Michael's talk, sort of the engine that allows us to compute these graded pieces is really graph complexes. So what we proved with Melody Chan and Soren Galatius is that H4G minus 6mg is non-zero for G not equal to 2, 4, or 6. And this last case is open. So for G equals 2 and 4, we know H4G minus 6 is 0. For G equals 6, I think we don't know yet whether H18M6 is 0 or not. We know that one graded piece of the weight filtration vanishes, or I guess we know 2 graded pieces. Okay, we know a bunch of graded pieces that vanish, but we don't know the whole story. And we know that the dimension of H4G minus 6mg grows, so at least exponentially with G. And we also found some sort of additional examples. So H15M6, H23M8, and H27M10 are not 0. And so again, so to prove non-vanishing results, or to prove exponential growth, it's enough to show that that's true for one graded piece of the weight filtration. And that's exactly what we did. And
Sam, when you wrote G equals 2, 4, 6, perhaps you meant not equal to? Also, you're getting a call.
Thank you, thank you. I declined the call, and yeah, G not equal to 2, 4, 6. Thank you. Good. Okay. So right. So why 4G minus 6? And so I may have said this out loud, and Michael mentioned this. So a theorem of John Harrer from the 1980s is that MG is a virtual. So the mapping class group is a virtual duality group, virtual dimension 4G minus 5. And so that means that any local system with rational coefficients has vanishing cohomology above degrees 4G minus 5. There is a local system, the Steinberg module, which has cohomology of rank 1 in degree 4G minus 5. And the Steinberg module for the mapping class group is the reduced homology of Harvey's complex of curves. So that's some infinite rank local system. And so that doesn't answer the question of whether the trivial local system has cohomology in degree 4G minus 5. So that would be the singular cohomology of MG. And the answer is that it does not. So this was proved independently by 2 different groups using very different methods, Church-Farb and Putman, and Morita, Sakasai, and Suzuki around the same time, 10 years ago. And they proved that H4G minus 5 mg is 0 for all G. So the significance of 4G minus 6 then is that this is the highest degree in which mg can have non-trivial cohomology. And for all but finitely many G, it does have cohomology there. And I should mention that this sort of abundance of cohomology in degree 4G minus 6 was not expected. So the conventional wisdom, so conjectured by Kontsevich in 93, and then so Kontsevich was writing about this in the context of formal non-commutative symplectic geometry, and he had infinite dimensional Lie algebras associated to certain operats, and that is the perspective that Morita, Sakasai, and Suzuki used in their proof. Church-Farb and Putman were coming at this from the point of view of combinatorial group theory, so generators and relations for the mapping class group. And so they were writing down group cocycles, or they were really looking at global sections of the Steinberg module. And so from their point of view, they made the same prediction, and the prediction was that if you fix K, then H4G minus 5 minus K mg is 0 for all g sufficiently large. Okay, so the idea was that there should be, even in the unstable range, there should be some sort of stabilization where now you're not fixing the degree as the genus grows, but you're fixing the distance below the VCD. And Churchfarb and Putman, they even gave stabilization maps. So they gave a map from H4G minus 5 minus KMG to the corresponding group for G plus 1. And they showed that if those maps are eventually isomorphisms, which means that the group stabilize, then they stabilize to 0. So this theorem is saying that conventional wisdom is not right, that those conjectures are not true, at least in degree 4G minus 6. And, okay, and so now let me explain the idea of the proof in a way that will sort of lead us towards the weight 2 work that Thomas Vilvacher and I have done more recently. So I mentioned that there's this additional structure on the cohomology of MG that comes from being an algebraic variety or being an algebraic stack. And I want to explain to you sort of where that comes from geometrically or topologically. And so we have a really nice modular compactification. There are, in fact, quite a number of nice modular compactifications of MG, but there's one in particular that I'm going to focus on, which is the Delaney-Mumford stable curves compactification. And this is nice in the sense that the boundary is normal crossings. And so, so this is a moduli space. The points in MG parameterize smooth projective curves of genus G, and the points in the boundary parameterize certain degenerations of those curves. So for instance, a curve of genus 2 could break into 2 pieces of genus 1, or it could stay irreducible, but pick up a node. So one, we could have some vanishing cycle, some loop that pinches off to 0, and then we could even get down to 2 rational curves meeting at 3 nodes, or we could have 2 singular rational curves that meet at a node. So these sort of 3 nodal curves. Okay, and there's some other strata that live in between, that one of these could become singular, or this could pick up 2 nodes. And so what we can do now is stratify by the combinatorial type. So there's some combinatorial or topological. So once we've picked up some nodes, if we sort of move in a family of things that have a certain node, well, that's a locally closed stratum. And then in the closure, all there is curves with more nodes. And whenever we have a stratification of a topological space, we have an associated spectral sequence. So you could think of this as when you have a closed subspace, you get an excision long exact sequence, and you have a stratification, you have many excision long exact sequences, you package them together into a spectral sequence. And in the spectral sequence on the E1 page, if we look at the kth row of that spectral sequence, E1.k is, let's say, built out of HK of, okay, and so, okay, HK of the stratum closures almost, okay, so the topological type corresponds to some dual graph, so call that G, and so you could look at MG, so the moduli space of stable curves with dual graph G, and you could take its closure. That will be some potentially badly singular closed subspace of of the Deligne-Mumford moduli space, and so we take its normalization. Okay, so it's built out of the direct sum over all G of HK mg bar tilde. The important thing is that these are smooth and proper. And so the HK of a smooth and proper variety or DM stack has pure weight K. And so this row is, everything there is weight K. And the theorem of Deligne says that, that there are no non-zero maps between Hodge structures of different weights. And so the spectral sequence collapses at E2. And so the cohomology of this row, so E1.k, this is a chain complex of Q vector spaces. It has some cohomology, and that cohomology is the kth graded piece of the weight filtration on the cohomology of Mg. So when I say that we're going to study the weight graded pieces of the cohomology of Mg, what I mean is we're going to study the E1 page of this spectral sequence one row at a time. And we're going to do that by understanding the cohomology groups of these stratum closures, normalized, and the natural maps between them. And so in my work with Melody Chan and Soren Galatius, we showed or observed that the zeroth row, E1.0, so the weight 0, and this spectral sequence is abutting to the compactly supported cohomology of Mg, so the Poincare dual of cohomology. Okay, so E1.0, so this is weight 0 compactly supported. So this is Poincare dual to the top weight cohomology of Mg. So this is isomorphic to the cellular cochain complex of delta G. So this is moduli of stable tropical curves. And then techniques that I think are well known to experts on graph complexes, like Karen Voigtman. So this delta G, this is the quotient of the simplicial completion of outer space by the action of out FG. And the quotient of the boundary of that simplicial completion is contractible. And so that gives rise to a quasi-isomorphism. So this is quasi-isomorphic to what Michael called GC of G. So this is Koncevich's commutative graph complex. And at that point, and now sort of the vast knowledge of the graph complex community sort of comes to the rescue, or really gives good results. So theorem of Thomas Wilvacher from 2015 is that the so direct sum over G H 2G of GCG is deep Teichmuller Lie algebra, and the theorem of, and so this H2G, so this is going to give rise to H2G compactly supported cohomology on Mg, which is Poincare dual to H4G minus 6, because Mg has real dimension 6G minus 6. So the 2G here corresponds to the 4G minus 6. And the theorem of Francis Brown is that inside of that GRT, so there's a conjecture of Deligne, Drinfeld, and Ihara that, so there's this free Lie algebra on the Soule elements, sigma 3, sigma 5, sigma 7, sigma 9. So one generator in each odd degree greater than or equal to 3. So this is supposed to be isomorphic to GRT, but what Francis Brown showed is that at least that free Lie algebra is present in GRT. So the expectation is that there's nothing else there. So this was, so half of conjecture of Deligne, Trinfeld, and Ihara. But the existence of that Lie algebra gives us the existence of many cohomology classes, and hence the existence of many cohomology classes on MG. And I think the sort of important or sort of fun thing to know about so sigma G pairs non-trivially with the class of a wheel in graph homology. So so this is W3, W5, and so on. And so to get the exponential growth that I mentioned, so now it's a question of computing the growth of this free Lie algebra. And you can do this by the Poincare-Birkhoff-Witt theorem. And you find that the dimension of this free Lie algebra with generators in these degrees, in degree D, grows like rho to the D, where rho is the real root of t cubed minus t minus 1 equals 0, so which is roughly 1.3247. And there's a rabbit hole that one can go down at this moment. So it turns out that this is sort of a famous number. It's a cousin of the golden ratio. This is the smallest piezo number. It's also called the plastic number. And so a piezo number is a real algebraic integer, necessarily of norm greater than 1, all of whose Galois conjugates have norm less than 1. And the piezo numbers are cousins of the Salem numbers. And both of them were studied extensively in the early to mid 20th century. So things that are known about the piezo numbers, the set of piezo numbers is closed. And so since it's closed and bounded below, there's a minimal element, and this is it, this real root of t cubed minus t minus 1. The first accumulation point of the piezo numbers is the golden ratio. And all of the piezo numbers less than the golden ratio are known. And every piezo number is a limit of Salem numbers. There's an open problem that the union of the Salem numbers and the piezo numbers should be closed. Other things that are known, so you can take the derived sets of piezo numbers. So take the piezo numbers, then the set of limit points of piezo numbers, then the set of limit points of piezo numbers. That sequence never terminates. So this is some sort of interesting point set topological subspace of R that comes from properties of real algebraic number field. So every real algebraic number field of degree n contains a degree n piezo number. And so if you sort of like this kind of, Da Vinci Code type thing. So if you take triangles with side length in ratio the smallest piezo number, so this row 1.3247, then you can arrange them to form a closed spirals. Okay, so that's a glimpse down that rabbit hole. As Michael mentioned, so here we're only looking at 1 degree of the cohomology of the graph complex. And now Michael has proved that, in fact, the total cohomology of the graph complex grows orders of magnitude faster than this one part. So there's a lot more out there to be discovered. And so let me mention just sort of one piece that that Thomas and I worked out. So we showed that H2G plus 3 of the graph complex is not 0 for G equals 6 and for G at least 8. And there what we did was we used so there's something, if you're thinking about the weight 0 compactly supported cohomology of MG, then it seems mysterious that you can put this together over all G and get a Lie bracket. But from the graph complex perspective, this is natural. And so what we do is, so the proof is show that the kernel of bracket with a 5 loop is contained in the kernel of bracket with sigma 3. So bracket with sigma 3 would keep you in the H2G. It would increase the genus by 3 and the number of edges by 6. But bracketing with a 5 loop increases the genus by 1, but increases the number of edges by 5. So that takes you from H2G to H2G plus 3. And
sorry, what do you mean by a 5 loop?
A pentagon.
Ah, okay.
A loop of length 5. Right, so this is, yeah, okay. So there are some versions of the graph complex that include these loops. There are some versions that don't, so maybe, so this is maybe in like FGC. Okay. And so then a corollary there is that H4G minus 9 mg grows exponentially with G. Okay, and it's non-zero for G equals 6 and for G bigger than or equal to 8. So that would be sort of a first example of an infinite sequence of non-vanishing odd cohomology groups on moduli spaces of curves. And let's see, so these two, these are the first 2 examples in that sequence. So 4 times 6 minus 9 is 15, 4 times 8 minus 9 is 23. So those things that were found just by experimental computation with graph complexes are the first in an infinite series. And one would expect that there are structures in the graph complex that explain the super exponential growth that Michael just told us about. This H27M10, that's something else. That's 4G minus 13. So I think it's natural to hope and expect that H27M10 is part of some infinite sequence, but that's an open problem. So I think there's a lot to play with and explore in those directions. Okay, and so all of that was about weight 0. So so the joint work with Thomas Billbacher that we did and posted to the archive during the pandemic was that we started studying so the second row of this spectral sequence, so E1.2 and its cohomology, which is GR2 of compactly supported cohomology of MG. And in some sense, we have a complete description. And so, and I'll highlight also the sense in which it's not complete. So it's complete in the following sense. So we have wedge 2 of the direct sum over G of weight 0 compactly supported cohomology of MG1. So that would be the cohomology of a commutative graph complex with one leg or one hair. And then we add the direct sum over all G of the weight 0 compactly supported cohomology of M G minus 1, 2. So 2 hairs, 2 legs, but now we take the anti-symmetric part. So the part on which S2 acts by the sign representation. Oh, excuse me. So that is outside the wedge 2. And then we take this and we take 2 copies of it. So we tensor with Q shifted by 3 plus Q shifted by 4. And then we give a map that we show is an isomorphism to GR2. So the weight 2 cohomology of MG. Maybe this should also be direct sum over G. Okay, so here both sides are bigraded by genus and cohomological degree. This shift is in the cohomological degree, not the genus. And okay, and so this is in some sense a complete description that we have completely described weight 2 cohomology in terms of something that is a priori simpler, which is the weight 0 cohomology. It's in terms of commutative graph complexes, but the sense in which it's incomplete is that our knowledge of these is quite incomplete. What we do know is that the weight 0 cohomology of MG, so both of these terms involve legs or hairs, but the weight 0 cohomology of MG injects into the weight 0 cohomology of MG1. And that is by pullback to the universal curve. And so in our applications that I'll describe, we only use this subspace. We use the image of weight 0 cohomology of MG in here. We take wedge 2 of that, and then we shift it by 3 and by 4, and we look at its image in GR2, and that's giving us non-vanishing and lower bound results on the cohomology of MG. Oh, and I should say that this injection is in general not surjective. It's not surjective already for G equals 8, but I can't tell you anything about the co-kernel. We just know that the Euler characteristics don't match. And so there has to be something else in weight 0 compactly supported cohomology of M81. Okay, so let me, so this table sort of summarizes what we can say so far about the vanishing and non-vanishing of cohomology groups of MG. And so here, so the white squares are vanishing groups, the black squares are non-vanishing groups, and the light gray squares are unknown. Dark gray is also non-vanishing. So what's happening here is, so up to genus 4, there's no gray, so we completely know those cohomology groups. And so M2 is contractible, so there's only H0. And I should say, so I've organized things so that H4G minus 5 is this column, H4G minus 6 is this column. So in the earlier discussion, you saw that the distance below the VCD was an interesting principle around which to organize. So that's how I organized the table. So here's H0M2, here's H0M3, H0M4. So this diagonal is H0. And then 2 steps to the left, here's H2M3, H2M4, H2M6, and so on. So this little zone of black and white stripes, here, this is the stable range. So that's the stable cohomology where we know non-vanishing from the kappa classes, and we know vanishing in between because we're in the stable range. Then we have these gray and black stripes. So the black is, these are even degree classes that we know are non-zero because there are polynomials in the kappa classes that are non-zero, even though we're outside the stable range and there are relations. Okay, so these classes are non-zero, but then in between, we don't know because we don't know, we're not in the stable range. There could be odd cohomology in between. Here is the first unstable class. So this is H6M3. So that was what was computed by Lohenge in 93. And here we have H5M4. So that's what was computed by Tomasi. Okay, and here we have H14M5. So that's the class of the 5-wheel. And here's that H15M6 and the H23 M8. So those were the first in this infinite sequence. So this column, so this is the H4G minus 6, and this is the H4G minus 9. So those are non-zero and weight 0. And then here's the outlier. So this is the H23M10. Okay, so we take this column, and this group, and we take wedge 2 of that, and then we apply the shifts. And that gives us these other columns as well. Okay, so all of these columns are non-zero because of weight 2, and this column has both weight 0 and weight 2, and all of them are growing exponentially, at least exponentially, and the rate of growth that we can prove is, again, that piezo number. Okay. Good. Okay, so now maybe I should start to, so let me start to give you the ideas of the proof and where you can see the types of graph complexes that arise. And just as in weight 0, we're going to start with something relatively naive that just is the second row, is the appropriate row of the weight spectral sequence, of the spectral sequence associated to the stratification of mg bar by combinatorial type. So I think these are now called Getzler-Kapranov complexes because complexes like this are very much at the heart of modular operads. And so the graphs that appear, so these are dual graphs of stable curves. So that means that each vertex has a genus. The sum of the genera plus the first Betti number of the graph is G, so the genus of the curves that we're considering. And so vertex of genus GV and valence NV is decorated by an element of the cohomology of the corresponding moduli space, MGV, NV bar. So moduli spaces of stable curves. And the sum of these cohomological degrees, that determines what row of the spectral sequence we're in. So for weight 0 cohomology or weight 0 compactly supported or top weight ordinary cohomology, we are looking at the case where every cohomological degree is 0. And that's why we were getting just something that was the cellular cochain complex of some combinatorial space because there were just H0s. But now we're taking the sum of the cohomological degrees to be 2. And so one thing that that I should tell you or remind you of is that the cohomology of moduli spaces of stable curves vanishes in degree 1. It also vanishes in degrees 3 and 5. So those are theorems of Arborello and Cornalba from 1998. And forthcoming work with Jonas Bergstrom and Karl Faber, we've shown that H7 and H9 also vanish. H11 does not vanish, and things get really rich and complex in higher odd degrees. But in any case, when the sum of the cohomological degrees is 2, there can't be any labels of degree 1. So that means that there's one special vertex labeled by an element of H2, and which is isomorphic to pick. And so this is, and all of this is from, so what's known about H2 is all from beautiful paper in IHES by Arborello and Cornalba in 98. And so sort of coming back to the analogy that we talked about at the beginning, so there are certain tautological classes in H2 of moduli spaces of stable curves. And Arborello and Cornalba showed that they generate, and they computed all relations among them. So H2 is then completely understood. And and so we're looking at these as graph complexes. So each graph is oriented, and the orientation is by a total ordering of the edge set. And the differential splits vertices or sprouts loops. So you can sprout a loop from a vertex of positive genus and decrease the genus of the vertex by 1. And then we have some decoration. So when you split a vertex, then you have 2 vertices of different genera, different valences, but the product of those 2 moduli spaces of pointed curves lives inside the original moduli space. So just like, so here, there's a natural map from M11 bar across M11 bar to M2 bar, which takes 2 pointed elliptic curves, glues them together, and views them as a stable curve of genus 2. And so if we have a cohomology class on M2 bar, we can pull it back to this product of moduli spaces and then take a Kunith decomposition. And so then we get a sum of factors, 1 on each component. So the differential splits vertices, sprouts loops, and pulls back cohomology classes under the natural maps between moduli spaces. So these bluing maps. Okay, and formulas for the pullbacks of tautological classes under bluing maps, all of that, again, was worked out in this paper of Arborello and Cornalba. So there's no new work that has to be done there. The work that has to be done is analyzing this graph complex. So this graph complex isn't quite in the form that that standard techniques are applicable. And so I do want to say a few words about how we massage this graph complex via a sequence of quasi-isomorphisms to get it closer to something that one can work with. But let me also give some examples of the types of classes so that one ends up seeing. So examples of non-zero classes in the weight 2 cohomology of MG. So we have this wedge product. So we could have, say, okay, so maybe let me do it. Okay. All right, so let's say we have gamma 1 in weight 0 compactly supported cohomology of MG1, and then we have gamma 2 in weight 0 compactly supported cohomology of MG2. And then what we do is we can draw an edge joining these two in every possible way. So and so then what we do is, so when we've drawn that edge, so we've added a marked point to some moduli space here, and we can take the psi class at that marked point. And then we can, so we have gamma 1, gamma 2, and at the other vertex, we can also, we have a psi class in the other direction. And so what we do is we take the difference between these two psi classes. And so here you can see the shift by 3. So the number of edges here is the number of edges in gamma 1 plus the number of edges in gamma 2 plus 1. And there's plus cohomological degree 2 for the psi class. So this is how you get the shift by 3. And the shift by 4 is a little more subtle. And so, of course, really gamma 1 is a linear combination of graphs, and gamma 2 is a linear combination of graphs. And so you have to extend this by linearity. But if you had a cocycle that was just one graph and one graph, then you would join them. And the wedge 2 comes from the sign convention on the orientations. And of course, that's a sort of graded wedge 2. Okay. All right, so that's, I hope that gives a, okay, so then let me just write then. So then we have gamma 1, wedge gamma 2 now is in GR2 H star compactly supported. And so if we gave the degrees of these, so if we had K1 and K2, this would be K1 plus K2 plus 3 mg1 plus g2. So that's sort of how we're building weight 2 cohomology out of weight 0 cohomology.
Sam?
Yes.
Your time is basically up. If you need a few minutes, that's okay. I just wanted to let you know.
Okay. Okay, let me just take maybe 2 minutes to sketch a couple of words. I hope that at least sort of orients you to the sort of motivation and structure of what we're doing. A couple of the main steps in the proof would be, so we want to filter by the number of vertices. And so there's a spectral sequence associated to that filtration. And the differential, the first differential for that filtration is only given by sprouting loops. And then we show that for almost all cases, so when the genus is positive and we're not in the G equals 1, N equals 1 case, those complexes are acyclic. So that allows us to eliminate vertices of positive genus. Okay, and so then there's a sequence of quasi-isomorphisms. So that gets you, I think, almost to the halfway point in the paper, but let me stop there.